Hi, welcome to Exothermic Reactions. This is how you make things burn. So, why do you want to do burning? Why do you want to work with this? Well, you need to know all about it because you want a little bit of fire. You don't want a big fire. When you have a big fire, it's a problem. So, this is a gas plant in Austria, and they have gas all the time. And this is them losing control of the gas in the gas plant in Austria. And you look at it and go, wait, that's not very useful for, like, say, heating people's homes at this point. I'm like, no, this is an inferno destroying equipment. So this is why little fire's good, big fire's bad. When we talk about exothermic, think about when you eat food. You're putting food in your mouth, your body is going to process that food, and part of that process is going to create heat. If you couldn't do that, your body, unless you live in 98.6-degree houses, your body is creating more heat than the air around you. And as such, that means that you have to eat more food just sitting there. You don't actually have to do anything. Just sitting there, you're burning thousands of calories, kilocalories basically, but you're burning thousands of calories just being alive by heating up your system and running all the systems inside your body. Down below we have wood. So wood plus fire equals charcoal. And in the process, you get the heat coming off as it breaks down the wood into charcoal. And if you notice in the background, of course, we have a giant forest fire, which is where it gets out of control. So these are exothermic reactions. Okay, so you have your wood up here. Here's your big ball of wood, and then you release the heat, and you end up with charcoal down here. So if you are looking at this, you'd say, well, and from a heat standpoint, you have a lot of potential energy in this wood, and then it loses a ton of it, and then your product doesn't have much energy or as much energy. You can't keep burning the ash of the wood. It's a one-way street. Once you've built it, once you've burned it, it's pretty much done. You can maybe burn it again if it was just charcoal, but at the time it gets to ash, when it's really fully burned, you're not going to burn the ash for much more energy. So this is an exothermic hot ice reaction where you often think of things being really hot, but in fact, you can start really, really cold. And as you get to room temperature, suddenly things want to be very reactive. So something like hot ice is going to actually bubble and give off a lot of heat, but it's not heat because it's going from a very low temperature to room temperature. So it's giving off, it's reacting to a lot of things, but it's not hot the way we would think about it. It's actually going to burn you with cold, which is a weird thought, but it's basically something like a hot ice, like ice or liquid nitrogen. When it gets into room temperature, it's actually very hot for it, and it's going to start to react very strongly. So you can have exothermic reactions that aren't technically feel warm to you. They can start from really cold and get warmer. So we've kind of explained fire, but I want to talk to you about how cool fire can be. So I want to think back to thousands of years ago. A guy named Callinicus was a refugee from Syria. Well, it wasn't Syria then, but it was that area. And he came to Byzantium, which is a place near the Mediterranean Sea. And he said to them, "Hey, you know what'd be really cool is you give me a job and let me stay here, and I'll give you the secret of Greek fire." Imagine a flamethrower in the Middle Ages. That's what Greek fire was. It was this thing that you could actually use a massive chemical exothermic reaction that took place and would catch other ships on fire. And this is what kept Constantinople free from being bothered, even when the rest of Rome fell, all this stuff. Hang on. So here we go. So, what was it? What was this stuff that was supposedly. So one was people thought, well, maybe it was gunpowder. Maybe Copernicus came up with gunpowder and he actually had like a cannon, but it doesn't really match with the stories about it. You can use potassium nitrite and you use fuels and you create nitrogen gas as a byproduct. So maybe. Then there's ammonium nitrate. Now, ammonium nitrate is quite explosive. So it could have been ammonium nitrate. So it could have been that stuff that they're using there. But again, I have to be honest, my preference is actually, I think that Callinicus came up with napalm, which was used in the Vietnam War. I think he came up with that solution way back when. So napalm, if you don't know about the Vietnam War, God bless you. The point is if you do, we did a lot of napalming in the Vietnam War, and it causes a lot of problems. Basically, it's got styrene. So polystyrene cups, the cups that keep things safe, mix that with a lot of gasoline and some benzene, and that's a very volatile chemical, and you basically use that to flamethrow on people. But because of the extra styrene, that nice foam cup, it sticks to people. It sticks and it keeps burning even if it hits water, which is what happened with the Greek fire. It would actually hit these boats, it would catch people on fire, and would catch the water on fire. And you can imagine just how freaked out you would be if you were like an invader with swords and somebody caught your boat on fire. You would go away and you would tell everyone else, stay away from the Byzantine Empire. What's really, really sad is they lost the recipe. I don't know how they lost the recipe because I'm like, I would have put that sucker in stone, but they wanted to kind of keep it secret, so they didn't put it in stone. But they lost the recipe, and that's why the Byzantine Empire eventually fell. So if you haven't exposed to Vietnam, you've probably seen this picture of this kid running down the middle of the highway because she had to throw her clothes off because the napalm was burning her. That's her on the right. She survived. She's not really a big fan of the Americans, but she did survive. And this is what it looked like. This is when you were firing. This is when you dropped napalm bombs on the Vietnamese. Is you'd see these enormous flaming, just absolutely insane. And of course, this is terrible for agriculture. This is terrible for anybody. This is a miserable way to do a war. We were basically frustrated because the North Vietnamese were kicking our butts, and we decided, okay, we're just going to bomb the place. It was a lot of madness happening. That was back in the 1970s. So one of the things that makes napalm so effective is it has a catalyst. It's got something that sets it off. It's like this. It's like the match for wood. Wood won't just spontaneously catch fire, we hope, but white phosphorus will make the napalm much more easily uh, flammable. So you basically, this is white phosphorus. This is what happens when when they're putting it on, and this is the breakdown, and it puts white phosphorus. Uh, that's that compound that's created. And here's what happened with the catalyst. So basically, if you've got something like wood down here, you need something to activate it. You've got to basically put the match. But there's lots of other catalysts. In your body, you'd use enzymes to break down your food. And it takes what normally would take a lot of energy. So if you want your wood pile to spontaneously combust, you'd better heat that sucker to several hundred degrees. Probably what? Fahrenheit 451 is what the spontaneous combustion of either wood or books, right? So Fahrenheit 451. It's around that temperature. So you'd have to combust, in order to make your wood combust, you have to bring it to 451 degrees, or you can add a match, which adds the catalyst, and then you can burn it at room temperature. So a catalyst is something that makes things burn or lets reactions take place much more easily. And of course, what we're talking about is potential energy, which is the energy up here that's potentially happening. You have a lot of potential energy at the top of a cliff, and then it becomes kinetic energy as you fall off the cliff because you got hit by this guy. And that's the way fireworks work, or bombs work, or everything works, is that you have potential exothermic energy goes to kinetic exothermic energy. Basically, it has potential to burn, and then it burns, and then you have a lot of burning happening. When I say a lot of burning, I mean a lot of burning.
Just after 6 p.m. local time on Tuesday, the 4th of August, an explosion ripped through Beirut's port.
So if you didn't know about that, that was basically a bunch of ammonium nitrate. That was a bunch of fertilizer that basically somebody put a spark next to. And that spark was sufficient to cause it to have a massive exothermic reaction. Remember, small fire good, big fire bad. So that's what happened.
Just after 6.
All right. Now, the problem is that this can happen to us as well. Very bad people did this in Oklahoma. It was called the Oklahoma City bombing. They took a bunch of ammonium nitrate and they actually bombed a federal building, which also had a daycare in it. So the reality is that exothermic reactions can be used to do very bad things. But exothermic reactions can be very, very helpful. They can heat your home, they can give you food and let you do things that you need food for. So there's a lot of good things that exothermic reactions can do as long as they're small and not big. Small fire good, big fire bad.